Welcome back. We have vector spaces and their subspaces. Now we measure their true size. Two questions do it. First, when is a set of vectors free of redundancy? When does no vector merely repeat what the others already reach? That is linear independence. Second, when does a set reach everything in the space? That is spanning. A set that does both, independent and spanning, is called a basis, the Goldilocks set. Not so few that it misses points, not so many that it wastes vectors. Then the theorem that anchors the whole subject: every basis of a given space has exactly the same number of vectors, and that common number is the dimension. Because it does not depend on which basis you pick, dimension is a real property of the space. Finally, once you fix a basis, every vector gets a unique address, its coordinates. We will count the dimension of Rn and of polynomial spaces, and watch one idea organize them all. Let's define independence carefully, because the definition is sharper than the intuition. A set of vectors is linearly independent if the only way to combine them and get the zero vector is to use all zero coefficients. Write c1 times v1 plus c2 times v2 on through ck times bk, and set that equal to the zero vector. If the only solution is every c equal to 0, the vectors are independent. If there is any other solution, some combination with not all coefficients, 0 that still produces 0, then the set is dependent. Here is the intuition behind the formula. Dependence means one of the vectors is a combination of the others. It is redundant, already sitting in their span, adding no new direction. Independence means the opposite. No vector is wasted. Each one points somewhere the others cannot reach. The clean test is always the same. Does only the trivial, all zero combination give 0? Independence is only half the story. The other half is spanning. A set spans the space if every vector in the space can be written as some linear combination of the set. The set reaches everything, leaving no vector out. Now put the two halves together. A basis of a space is a set of vectors that is both linearly independent and spanning. Independent, so there is no redundancy, nothing repeats. Spanning, so there is full coverage, nothing is missed. Think of it as a balance. If you have too few vectors, they cannot possibly reach the whole space, so they fail to span. If you have too many, some must be redundant, so they fail to be independent. A basis sits exactly on the boundary between those two failures. Said another way, a basis is simultaneously the smallest set that still spans the space, and the largest set that is still independent. That double description is why a basis is the right notion of a coordinate system. Here is the theorem that makes everything solid. Suppose a space has a basis with n vectors. Then every other basis of that same space also has exactly n vectors, never more, never fewer. The count is forced. That common number is called the dimension of the space. Because it does not depend on which basis you happen to choose, dimension is a genuine property of the space itself, a single number you can attach to it. Why is the count forced? The engine is the replacement idea, sometimes called the exchange lemma. If a space is spanned by n vectors, then any collection of more than n vectors has to be linearly dependent. You cannot fit more independent directions than the spanning set provides. So no independent set can be larger than a basis, and no spanning set can be smaller. Squeeze those two facts together and every basis is pinned to the same size. That is the precise sense in which a space has a well-defined dimension. A basis does something wonderful. It gives every vector a unique address. Fix a basis. Call its vectors b1 through bn. Then any vector v in the space can be written as a combination of the basis vectors, c1 times b1 plus c2 times b2, and so on. The key word is unique. There is exactly one choice of those coefficients. We collect them into a column called the coordinate vector of v in that basis. Why are the coefficients unique? That is precisely independence. If a vector had two different representations, subtracting one from the other would give a non-trivial combination of the basis vectors equal to 0, which independence forbids. So uniqueness and independence are the same statement viewed from two sides. The consequence is sweeping. Once you fix a basis, every n-dimensional space, whatever its vectors are made of, turns into Rn, with each vector standing in for its list of coordinates. The abstract space and the familiar tuple space become two views of one thing. The cleanest example is the standard basis of Rn. These are the unit vectors along the axes. E1 is 1 in the first slot and 0 everywhere else. E2 is 1 in the second slot and 0 elsewhere, and so on up to En. Are they independent? Combine them with coefficients c1 through cn, and the result is simply the vector whose components are c1 through cn. For that to equal the 0 vector, every coefficient must be 0. So yes, independent. Do they span? Any vector with components a1 through an is just a1 times e1 plus a2 times e2, and so on. So yes, spanning. Independent and spanning, so the standard unit vectors form a basis. Since there are n of them, the dimension of Rn is n, exactly as you would hope. And notice the coordinates of a vector in the standard basis are nothing but its ordinary components. The standard basis is the reason components and coordinates feel like the same thing. In this special basis, they are. Now, a basis with no arrows at all, polynomials. In the space of polynomials of degree at most n, the natural basis is the list 1, x, x squared, and so on up to x to the n, the pure powers. Do they span? Every polynomial of degree at most n is, by definition, some combination of these powers. A constant times 1, plus a coefficient times x, plus a coefficient times x squared, and so on. So yes, are they independent? Suppose a combination of them is the zero polynomial, meaning it equals 0 for every value of x. A non-zero polynomial of degree at most n can have at most n roots, so the only way to vanish everywhere is for every coefficient to be 0. That is exactly independence, so the powers form a basis. Count them 1x up to x to the n, that is n plus 1 vectors. So the dimension of this polynomial space is n plus 1. For instance, the quadratics, degree at most 2, have basis 1x x squared, so their dimension is 3. Polynomials are just coordinates in disguise. One more distinction before the examples. A space is called finite dimensional when it has a basis with a finite number of vectors, and then the dimension is just that count. We have already met 3, our n has dimension n, the polynomials of degree at most n have dimension n plus 1, and the matrices with m rows and n columns have dimension m times n, since you need one basis matrix for each entry. But some spaces have no finite basis at all. Take the space of all polynomials with no bound on the degree. The natural basis is 1x x squared x cubed and on forever. The list never ends, and no finite piece of it can span every polynomial. That space is infinite dimensional. Most function spaces and sequence spaces are infinite dimensional too, and they are the home of advanced analysis. This course lives mostly in finite dimensions, where bases are finite and dimension is a plain whole number. But notice the definitions never demanded a bound. The ideas reach further than the examples we draw. Let's see independence in three-dimensional space. On the left, 3 arrows leave the origin pointing in 3 genuinely different directions. Because no one of them lies in the plane of the other 2, they fill out a solid chunk of space. The shaded box is the region they span, and in fact, their combinations reach every point in three-dimensional space. These 3 are independent, and they form a basis. On the right, 3 arrows that all happen to lie in a single tilted plane, shaded faint red. The third arrow is a combination of the first 2. It adds no new direction, because it is trapped in the same flat sheet. Their combinations can never escape that plane, so they fail to span all of space, and the set is dependent. That is the whole picture of dependence. The vectors collapse into something lower dimensional than they should. Independence means the arrows genuinely spread out. Dependence means at least one of them is redundant, lying inside the span of the rest. Here is why coordinates depend on the basis you choose. Picture a single fixed point in the plane, marked in gold. Lay down the familiar square grid first, built from the standard basis vectors along the axes. In that grid, you reach the point by going 3 steps along the first axis and 1 step up the second, so its coordinates are 3, 1. Now lay a different grid over the same plane, one built from 2 slanted basis vectors that are not perpendicular. The grid lines tilt, and to reach the very same point you now take some other number of steps along each slanted direction, giving completely different coordinates. The point never moved. What changed is the basis, and with it the address. This is the crucial idea. A vector is one fixed thing, but its coordinates are relative. They are a description in terms of a chosen basis. Change the basis and the same vector wears a new list of numbers. Choosing the right basis to make a problem simple is a recurring theme for the rest of the course. First worked example, test 3 vectors for independence. Take v1 equal to 1, 1, 0, v2 equal to 0, 1, 1, and v3 equal to 1, 0, 1. Set a combination of them equal to the 0 vector and read off the components. The first components give c1 plus c3 equals 0. The second components give c1 plus c2 equals 0. The third gives c2 plus c3 equals 0. Now solve. From the first equation, c1 equals negative c3. From the second, c2 equals negative c1, which is c3. Substitute into the third, c2 plus c3 is c3 plus c3, which is 2 times c3, and that must be 0, so c3 is 0. Then c1 and c2 are 0 as well. The only solution is all coefficients 0, so the 3 vectors are independent. And 3 independent vectors in 3-dimensional space automatically span it, so they form a basis. Any n independent vectors in an n-dimensional space are guaranteed to be a basis. Second worked example, trim a spanning set down to a basis. Start with 3 vectors in the plane, u1 equal to 1, 2, u2 equal to 2, 4, and u3 equal to 0, 1. These 3 certainly span their span, but they may carry redundancy. Look closely, u2 is exactly 2 times u1, same direction, just longer. So, u2 is redundant, it adds nothing the others do not already reach, and we discard it. That leaves u1 and u3. Are they independent? 1, 2 is not a scalar multiple of 0, 1. They point in genuinely different directions, so yes, independent. 2 independent vectors in the 2-dimensional plane must span it. So the basis we extract is 1, 2 together with 0, 1, and the span of the original 3 vectors is 2-dimensional. It is all of the plane. The lesson: to get a basis from a spanning set, throw away vectors that are combinations of the ones you have kept, until nothing is redundant. Third worked example, write off a vector's coordinates in a non-standard basis. Use the basis of the plane whose first vector b1 is 1, 1, and whose second vector b2 is 1, negative 1. Take the vector v equal to 4, 2, and find its coordinates in this basis. That means finding coefficients c1 and c2 so that c1 times b1 plus c2 times b2 equals 4, 2. Matching components gives 2 equations, c1 plus c2 equals 4, and c1 minus c2 equals 2. Add the 2 equations, 2 times c1 is 6, so c1 is 3, then c2 is 1. So v equals 3 times b1 plus 1 times b2, and its coordinate vector in this basis is 3, 1. Notice that is different from the vector's ordinary components, 4, 2, which are its coordinates in the standard basis. Same vector, 2 different addresses, 1 for each basis. Finding coordinates always comes down to solving a linear system, exactly the machinery we built earlier in the course. A short history. The ideas of independence and dimension, like the vector space itself, trace back to Hermann Grassmann in 1844, who already worked with independent vectors and dimension in arbitrary numbers of dimensions, decades before the rest of mathematics caught up, and largely unread at the time. Toward the end of the 19th century, Richard Dedekind made notions of rank and dimension precise while studying systems of equations and the structures we now call modules. Then, in 1913, Ernst Steinitz proved the decisive technical result, the exchange lemma, the careful argument that lets you swap basis vectors one at a time and concludes that every basis of a space must have the same number of elements. That lemma is exactly what makes dimension well defined. From there, basis and dimension became the backbone of the subject, coordinates, rank, and every matrix decomposition still to come, all rest on the fact that a space has one honest size. Next, we turn that machinery on matrices themselves. Let's recap. A set of vectors is linearly independent when the only combination of them equal to the 0 vector is the all-0 combination, meaning no vector is redundant. A set spans a space when every vector in the space is a combination of the set. A basis is a set that is both independent and spanning. The just right collection, smallest that spans, largest that stays independent. The central theorem is that every basis of the same space has the same number of vectors, and that number is the dimension. Once you fix a basis, every vector has a unique coordinate vector relative to it, which turns the abstract space into Rn. The standard basis of Rn is the unit vectors along the axes, so Rn has dimension n. The polynomials of degree at most n have basis 1, x, up to x to the n, so that space has dimension n plus 1. Next episode, we apply basis and dimension to matrices and meet the 4 fundamental subspaces, where these counts lock together into the big picture of linear algebra. Today we learned to measure a vector space. A set of vectors is linearly independent when the only way to combine them into the 0 vector is to take every coefficient to be 0. If some non-trivial combination gives 0, the set is dependent, and at least one vector is redundant. It already lives in the span of the others. A set spans a space when every vector in the space is some combination of the set. A basis is a set that does both at once independent, so nothing is wasted, and spanning, so nothing is missed. The central theorem is that every basis of the same space has exactly the same number of vectors, so that number is a genuine property of the space. We call it the dimension. Once you fix a basis, every vector has exactly one set of coefficients that builds it, and those coefficients are its coordinates relative to that basis. The standard basis of Rn is the set of unit vectors along the axes, so Rn has dimension n. The polynomials of degree at most n have the basis 1, x, x squared, up to x to the n, so that space has dimension n plus 1. Worked examples test independence, extract a basis, and read off coordinates. Historically, the rank and dimension story runs through Grassmann, Dedekind, and Steinitz, whose exchange lemma makes dimension well defined. Next episode, the 4 fundamental subspaces of a matrix. If you got something out of this, please like the video, drop a comment with what clicked for you or what didn't, and subscribe for more educational videos. Every like, comment, and share helps push this work to more learners, which is what this channel is really about. Thanks for watching. See you in the next one.